So, again you see that expanded ACSR conductors are used in extra high voltage transmission line, right. So, by the use of a filler or such as paper or hessian, right, between various layers of strands, so as to increase the overall conductor diameter to reduce the corona loss and electrical stress at conductor surface, right. And bundle conductors are commonly used in extra high voltage transmission line to reduce the corona loss and also reduce the radio interference with communication circuit, right. So, this is that your what you call expanded ACSR conductor are also used for your extra high voltage transmission line. So, next is that inductance of composite conductors, right. Suppose this is your figure 6, a single phase line say consisting of two composite conductors X, this is actually I have written X, composite conductor X. Suppose you have A, B, C, D up to n number of conductors in this group composite conductor. Here also A dash, B dash, C dash up to M, you have composite conductor another group, you have m number of conductors, and we are calling this is composite conductor X and this is calling composite conductors Y, right. And what we are doing is that we are assuming that all these conductors they have their your radius remains same. So, for this group as composite conductor X we are taking, for this group radius of this conductor, all these conductors we are assuming Rx, small r suffix x, here it is Rx, right. And here also that it is A dash, B dash, it is a group Y. Similarly, this Y having m identical conductors, right, their radius is Ry, here it is Ry, here it is Ry, right. And another thing is that, and suppose this group, this total current, right, that this thing the current in this group is I, right, referred into the page, and that means and the return current is minus I, that means if one is entering the page another is leaving to the page. So, this current total current actually I, and here it is return, I mean it is something like this, there should not be any. Suppose you have, I am just for the sake of understanding I have this thing, suppose this is suppose if you have suppose A, B, C, N, this kind of four conductors, right. Suppose you have this much of conductors and this is the current I, all the radius of this conductor is your what you call, we assume that it is your Rx. So, total current is I. So, each conductor will carry current I by N, because they all are in parallel and we assume they are all similar conductors. So, each conductor will carry current I upon N. So, here in that group you have n number of conductors, right, that means in this group total current is I total, but after that current is getting divided in equally in each conductor. Therefore, each conductor actually is carrying I by N current, right. So, later we will see next page, and here also the current is I, but it is a return path, right. So, if this current positive is I by I, this current will be minus I, and each current returning it will be minus I by m, because here you have m number of conductors, right. That means so we have assumed that current is equally divided among the subconductors. So, thus each subconductor of X carrying a current I by N, I just told you, and each subconductor of Y carrying a current minus I by M, minus sign it is a return path, that is why minus I by M. Now, we will use this equation 46, we will use this equation we will use again and again. Now, this 46 equation number, this is generalized flux linkages, this equation we will use, right. So, applying equation 46 to subconductor A, that means for this conductor, say so many conductors are here, we are applying for say for this conductor A, right. Therefore, this formula if you use, then you will see lambda A, we are now replacing for conductor A, lambda A is equal to 0.4605, current is your, instead of I it should be I by N, each conductor is carrying I by N, right. So, I by N, then your log 1 upon r dash rx dash, because rx is the radius of the subconductor in group X, right. So r dash x plus all the distances log 1 upon dab. Here it was given in terms of general one, j is equal to 1 to n, j not is equal to ij log 1 upon dij, the general thing, but ij all can be replaced to a, b, c, m, and write this, right. So this one we can write log 1 upon dab, that means this distance within this group, dab, then log 1 upon dac plus log 1 upon your ab ac, then log 1 upon dad, right, up to plus log 1 upon dan. The first this thing is all the distances from a, from subconductor a to all other conductors in this group. That is why log 1 upon dab plus log 1 upon dac plus log 1 upon dac plus dot plus log 1 upon dn. So this is the first thing within that a to b, a to c, a to d dot a to n, all the distances, right, using this formula only, Now next one is this return path is also there, its current is minus I by m. So that is why next one is your minus 0.4605 minus I by m, then log 1 upon daa, right, that is your daa dash, that means mutual distances a dash, then you look here a dash, then you look ab dash plus look ac dash up to plus log 1 upon dam, mutual distances, right. So this is within the group, this is between that group, right. So first term is all like this, second term is only the daa dash, ab dash, ac dash up to am, right, and minus sign because this is a return path. So this is only the expansion of this particular equation, right. So I hope you have understood this, right, very simple actually. This is one is incoming, another is outgoing return path, only you have n number of conductors there, but if n is equal to m, then different issue, right, but this term will remain as it is. This is within the group, this is between the group, the distance between the group, right. So now we will simplify this equation. Therefore this term lambda equal to this term in, they all should be log 1 upon rx plus log, all these things can be written as log 0.4605 I by n log 1 upon rx dash into dab into dac into dad up to dan, right. And next now this is actually 1 upon da dash log of 1 upon da dash plus log upon 1 upon dab dash, like this. So rather than you take this one, you make plus, right, and this 1 upon da actually you can write da to the power minus 1 on dab to the power minus 1, so all minus 1 will come, ultimately will be plus. So 0.4605 I by m, you can log then daa dash into dab dash into dac dash up to dam, right. So this plus, because this 1 upon da we have made da, 1 upon dab, right. So just you make this thing like this way, right. Next these two you can write that your 0.4605 I, this 1 upon n is here, where 1 upon m is here. So log of all these thing and this power to the power 1 upon n, right. And similarly this one also 1 upon m is here, I by m. So this power to the power 1 upon m, right. Therefore it can be written as lambda a is equal to 0.4605 I log daa dash into dab dash into dac dot dm to the power 1 upon m rx dash into dab into dac into dad up to dam to the power 1 upon n. This is equation 49. I think it is understandable to you, right. So, now therefore, inductance of subconductor A is that flux linkage L A is equal to lambda A, and each conductor is carrying current I upon N divided by I upon N. Do not make I, because I is the total conductor. Each conductor is carrying current I upon N. So, it should be lambda A upon I upon N is equal to, then lambda you know is equal to N into 0.4605 log the same expression dA dash into dAb dash into dAc dash up to dm to the power 1 upon m, then Rx dash into dAb into dAc into dAd up to dN to the power 1 upon n. This is equation 50, right. Now, the average inductance of any one subconductor of composite conductor X can be given as L average, can be given as LA plus LB plus up to dot Ln divided by N. This is equation 51, right. And since conductor X is composed of n subconductors electrically in parallel, its inductance is L average by N. The idea is something like this, no. Suppose you have that average inductance of any subconductor, this is the average inductance of any subconductor, and if you have so many things are parallel, right, so many things are parallel dot 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 up to n, it all are L average, then L average, all are L average, then their equivalent is then L average by N, right. So, all are electrically parallel. So, that is why L average will be your total, that means L average we got first, right. Then total, this is the composite X, that conductor group X. So, that is L average N, L average divided by N, right, because everyone has average inductance L average we are computing here LA plus LB up to this up to Ln by N, because in group X n number of conductors are there, right. Therefore, and all the conductors electrically are in parallel. I showed you also this, all conductors are in parallel, right. The total current I, each conductor is assuming current I by N, right. Therefore, this Lx is equal to that group since conductor X is composed of n subconductors electrically in parallel, it induct, that means group your what you call group X, that inductance Lx is equal to L average by N is equal to La plus Lb plus Lc up to Ln divided by N square, because L average is La plus Lb up to Ln upon N, and this one is equal to, here N is also there. So, if you substitute L average this one, it will become N square, it is 52, right. Therefore, now substituting the values of La, Lb, Lc and Ln in equation 55, we have computed only La, right. So, if you like this, if you compute La, Lb, Lc all sort of like this, cannot be made it here only, right. So, if you can make yourself Lb, Lc like this, right. So, if you substitute all the values of La, Lb, Lcn in equation 52, then in this equation you substitute, right. Remember, if you substitute La, Lb, Lc, all will be function of n into this term. So, as soon as you substitute here, that n will be everywhere, La, Lb, Lc, 1 n will be cancelled here, only 1 n will be remain, not n square, only n will be remaining, right. So, that is why if you substitute, this equation can be written as 0.4605 log dm upon dsx millihenry per kilometer. I will define what is this, right. So, and as you substitute that this all La, Lb, Lc all function of n, that means it will not be n square, because 1 n will be cancelled, only n will be there, right. So, in that case what will happen, that dm is equal to, that is daa dash dab dash dot 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 dm, then this is for subconductor A to all the mutual distances of the other group. Similarly, for conductor your B in group X to the distances to all conductors in group Y, right, that is BA dash, BB dash and so on up to your DNA dash, DNB dash, DNM, right, and to the power 1 upon Mn, because 1 upon n I told you that when we will try to find out this one, only n will be there. If you make all this is function, this is n, 1 n will be cancelled, 1 n will be there. So that is why, and earlier it was 1 upon n, now it will be multiplied by your 1 upon n into 1 upon m into 1 upon n, it will be 1 upon mn, right, it will be 1 upon mn, little bit you try yourself, right. Similarly, for self one, it is within that group DA, DAB, DN, for the subconductor A to all its distance in the group say X, right, A, AB, AN. Similarly, from BA, DBB, DBN up to solve product up to DNA, DNB, DN, it will be 1 upon n square, because here it was 1 upon m. So because of that, another 1 n will be there to find out your Lx, this thing, to find out the this expression of Lx. So because of that, that is 1 will go to 1 upon n will be there when we will find out the average one. So it will be 1 n will be there, so it will be 1 upon mn and it will be 1 upon n square, right. That is why here it is 1 upon mn and here it is 1 upon n square, right. And this is equation 55. I hope you have understood this one, right. This is distance of a particular conductor in group X to that all this thing your what you call conductors in group Y, that is why A dash, AB dash, AM, BA dash, BB dash, like this up to the power 1 upon mn, 1 upon mn, and this is within the group. So DA, DAB, DN, DBA, DBB, DN and so on, this will be 1 upon n square, right, and this is equation 55, where DA, DBB up to DNN they are basically fictitious radius, that is Rx dash of group X, right. Therefore, this D, now this DM, that is your this one, this DM, that is DM and DSX, right. See, DM is the mnth root of the mn terms, which are the products of all possible mutual distances. I told you these are all mutual distances between one conductor in group X to all the conductors of the group Y, that is why A dash, AB dash up to M, BA dash, BBB dash, BM for bth conductor. Similarly, for nth conductor in group X to other conductors in group Y, NA dash, NB dash, these all are product to the power 1 upon mn, right. So when it is mutual distances coming in group A, m number of conductors are there, group Y, y number of conductors are there. So total possibility is m into n, that is why dm is the mnth root of the mn terms, which are the products of all possible mutual distances from the n subconductors of conductor X, that is group X, to m subconductors of conductor Y, right. It is called the mutual geometric distance, that is mutual GMD. This is called, this dm is called that mutual geometric your what you call a distance, right. So called mutual GMD, right. Similarly, DSX is the n square root of the product of n square term consisting of Rx dash, that is DA, DBB, all are basically fictitious radius Rx dash, and you have your suppose in a group n number of conductor your subconductors are there. So it is n square root of the product of n square terms, right, because it will be n into n, right, consisting of Rx dash of every strand times the distance from each strand to all other strands within group X. The DSX is defined as the self geometric mean distance, this is called self GMD of conductor X, right. So one is mutual GMD, another is self GMD, right. So for everything we need two things to find out the inductance, one is mutual GMD, another is self GMD, right. I hope you have understood. Therefore, similarly for conductor Y, similarly for conductor this thing that group Y, the inductance of the composite conductor Y can also be determined in a similar manner. So in this case, as it is one is group X, another is group Y, so there will be no change in mutual GMD, it will remain same, that means dm will remain same, right. So, mutual GMD dm will remain same, but your self GMD dsy will be different. This dsy will be calculated same as before. The way we have made it for group X, that conductor composite conductor X, similar way you have to make it here for composite conductor Y. Not shown here, this is up to you, little bit this thing up to you, right. So, next one is, I hope you have understood, little bit practice is necessary, right, and little bit understanding is also necessary. So, next is that inductance of 3-phase transmission line with symmetrical spacing. So, here we have assuming that we have a 3-phase transmission line, phase A, phase B, phase C say, and symmetrical spacing d is the distance, is a, it is conductors are say you are sitting at the corner of a your equilateral triangle. So, this is first we have assumed like this, after that we will generalize, right. So, this 3-phase line with symmetrical spacing d distance same, and the radius is also r for each conductor r, right, and this is your. So, this is figure 7. So, figure 7 shows the conductors of a 3-phase transmission line with symmetrical spacing, a radius of the conductor we have assumed that it is r, right. So, again here we will use the same equation, that equation 46, that means same equation, this equation 46, again you will put this equation. If you try to understand again and again, if you can understand this equation, from this equation you can derive everything, right. So, this equation 46, the total flux linkage of conductor phase A is given by lambda A for phase A only. Here it is II log 1 upon Ri. Suppose for I is equal to A comma B comma C, 3 phases are there, A, B, C. Suppose I is equal to A, I mean I small I, this is A, right, A, B, C, 3 phases are there. So, lambda A is equal to 0.4605 into IA, instead of here it is general one, that IA log 1 upon R dash plus IB distance same. So, it will be log 1 upon D plus IC log 1 upon D, right. Otherwise, it should have been DAB, DBC like that we will see later. This is equation 56, but in this case distance are equal, so things are easy, right. So, lambda is equal to 0.4605 IA log 1 upon R dash plus IB log 1 upon RD plus IC log 1 upon D. This is 56, assuming that balanced 3-phase current, we are assuming therefore IA plus IB plus IC is equal to 0, therefore IB plus IC is equal to minus A. That means this equation, that just hold on, this equation lambda A is equal to 4605 IA log 1 upon R dash plus IB log 1 upon D plus IC log distance same, this is from equation 56, right, is equal to 0.4605 then IA log 1 upon R dash, right, plus IB plus IC, you outside you write log 1 upon D, right, and IB plus IC is a balance condition. So, IB plus IC is equal to minus IA, you put here minus IA log 1 upon R dash minus IA log 1 upon D, right. So, this one you can write 0.4605, right, IA common, right, log 1 upon R dash, now minus it is 1 upon D, so we are writing log D. So, minus has become plus, is equal to 0.4605 IA log D upon R dash, right. So, that thing, that is the thing that we are substituting using equation this 56 and 57, this 56 and 57, right. So, we are writing that just now I shown this expression, right. So, we can write lambda is equal to 0.4605 IL log d upon r, right. It is milliweber turns per kilometer, right. So, this is equation 58. Therefore, inductance L A is equal to lambda A upon I A. So, I A will not be there now. So, is equal to 0.4605 log d upon r dash millihenry per kilometer. This is equation 59, right. So, because of symmetry, right, because of symmetry lambda A is equal to lambda B is equal to lambda C, because it is an equilateral triangle actually, and hence these inductances are identical, that is L A is equal to L B is equal to L C, right. So, they are same because it is symmetrical spacing, right. So, I hope up to this it is it will be this thing understandable to all of you. I mean this calculation of inductance, right. And after this what we will do now, inductance of 3-phase transmission lines with asymmetrical spacing. Now, that your what you call that it is not symmetrical now, right. Therefore, with asymmetrical spacing, even with balanced currents, the flux linkages and inductance of each phase are not the same. In fact, the spacing is not symmetrical, it is asymmetrical spacing. So, even if that current is balanced, right, but flux linkages and inductance of each phase will not be the same. So, in that case, suppose you have a 3-phase line, this is phase A, phase B, and this is phase C, phase A, this is phase B, this is phase C, right. So, distance between the phase A and B is DAB, phase A and C is DCA, and B and C is DBC, right. So, now the DAB, DBC, DC are different. So, using that same formula, that equation this 46, again and again we will use this one, right. Use this equation again and again, then everything is easy. Using this equation 46, right, you can write lambda A for the flux linkage of the conductor in phase A is equal to 0.4605 I A log 1 upon r dash plus I B log d A B 1 upon d A B A to B plus I C log 1 upon d C A, the distance is A to C, we are writing A B B C C A, basically A to C is A C, we are writing D C A. So, I C log 1 upon D C A, this is equation 60. Similarly, for phase B you can write lambda B is equal to 0.4605, then I A, then log 1 upon d A B, right, because B to A, so your I A distance is A to B DAB, IA log DAB. As soon as you are coming here IB plus 1 upon IB, that it will be log 1 upon R dash IB into, and when it is plus IC log 1 upon DBC, right. So, between this. Next is, this is equation 61. Similarly, lambda C is equal to 0.4605 IA log 1 upon DCA, right. This is now for lambda C plus IB log 1 upon DBC, right, that is 1 upon DBC plus IC log 1 upon R dash. When IA, IB, IC is coming 1 upon R dash, right. This conductor may have different radius also, R1, R2, R3. In this case, this should have been R dash, this should have been RB dash, this should have been RC dash, but we have assumed they are same, and just I am using this formula only, right. So, this generalized formula you try to understand again and again, I am telling this, right. So, that means this is equation 62. So, you have got lambda A, lambda B and lambda C, these flux linkages of phase A, phase B, phase C conductors, right. Now, or in matrix form, if you put, or in matrix form if you put, then it will be lambda A, lambda B and lambda C, right, and it will log 1 upon r dash, log 1 upon DAB, log 1 upon DCA, log 1 upon DAB, log 1 upon r dash, log 1 upon DBC, log 1 upon DCA, log 1 upon DBC, log 1 upon r dash into IA, IB, IC. This is your 63. Therefore, symmetrical inductance matrix L is given by, right, because everywhere you will divide for lambda A, you will divide by it IA, for lambda B you will divide it by IB, and for lambda C you will divide by IC, such that LA, LB, LC all will get. So, that is why in matrix form if you write, only this matrix will be there. So, L is equal to, if you do so, L is equal to, hold on one thing, here lambda A, lambda B, I have missed one thing, that 0.4605 I have missed it, right. It should be multiplied by, this should be multiplied, I am making it here somewhere, this should be multiplied by 0.4605, right. I have missed it actually, right, it should be multiplied. So, because here it is 0.4605, 0.4605, 0.4605, so I have missed it, right. So, therefore, L is equal to L means LA, LB, LC, right, is equal to 0.4605 log 1 upon r dash, log 1 upon DAB, log 1 upon DCA, log 1 upon DAB, log 1 upon r dash, log 1 upon DBC, log 1 upon DCA, log 1 upon DBC, log 1 of millihenry per kilometer.